Okay, shall I start? So, thanks for coming again. I don't know if you were excited by the talk yesterday and came again, or you want to see the talk after me, but in any case, good to have you back again. So, okay, just to remind you, so we were talking about this programming language, and the goal was really to present you, well, give you an idea how to design programming language that would be specific for wireless applications, and also give you some insights in how compilers design, how it can do this processing very fast. So where I left yesterday was one optimization, which was the lookup tables. I believe you heard a little bit about from Kuhn last week. So the advantage here that we kind of follow up on their work is really being able to do it automatically from your code without really needing to think about where to do that and letting compiler do it for you. After that, I'm just going to give you a little bit of code examples and show you how these optimizations are all being done. And then we're going to go over Wi-Fi receiver and transmitter. And I'm going to give you a brief overview of each block. And I'll try to demo you each block in Ziria, give you the code, how it looks like, explain you how it's implemented. And so on one hand, give you an idea why Wi-Fi is designed as it's designed, and then on the other hand, show you what kind of optimizations you have to do because to make it run real time in Sora, and also kind of show you how you can do all these things together very easily, right? So the examples are very small, and we should be able to go to them in real time, right? And you should be able to understand, right? So that's the hope. And right, so again, if you have any questions, just stop and ask me. So I'm just going to come again back to these optimizations. That's where we stopped yesterday. So basically, in particular, the Wi-Fi transmitter, you have lots of operations that are executed at the bit level, right? And so what we said is that we want to be able, if we have an operation that is executed at the bit level, it's very inefficient if you do it on CPU, right? It's meant, and the design of the whole thing is inherently done for FPGAs and ASICs. So the way you do that is, basically bit level is normal. On CPU, it's not normal because you're working on at least bytes, if not more, right? So here, the thing what you want to do is, here's an example of a scrambler. So the scrambler does, we had this yesterday, I'm just going to briefly repeat. So you're taking one bit of from the input, and then you are doing small bit state machine. So there's this scrambler state, which is 7 bits. And then there is so basically you take this, you calculate a state, a temporary variable from this scrambler, you shift the scrambler, basically you move 0 to 5 to 1 to 6, and basically you append the last bit, you put whatever the new scramble state is, okay? So it's a kind of random number generator, LFSR, I can't remember what the abbreviation is, but it's kind of a standard thing where you kind of generate pseudo-random sequence through these shifts, and then you simply XOR your input with this output of the sequence, and you output it out. And so the first thing that was kind of interesting here is that the code is kind of quite obvious. There's it kind of maps directly to what is in Wi-Fi specs. So that was one of the goals. You have to, when you write the code, it should be very clear. Now the question is, how do we do it fast, right? So there was optimization we discussed yesterday. First was the vectorization. So the fact that we can do this, we can automatically figure out this could be done in the loop of 8. And then we want to optimize things inside. So first, we vectorize this and we say, okay, now I take this code inside and I put a for loop around it, right? And I realize that in a for loop around it, basically it's a very simple transformation, kind of obvious, but it's automatic, right? You don't have to do it. You create an array, and for each element of an array, so this is an array and the output is an array, you just do this 8 times, as simple as that. But you need to figure out, you need to do it automatically, right? And then the next thing is really, if you look at this array, you need to realize that it could be mapped to a lookup table. So again, a lookup table is basically something you do in FPGAs. You say, okay, I'm looking at the inputs to this piece of code, look at the outputs of this piece of code, and I realize that instead of running this thing here, my input and output space is small enough to that I'm able to put it in a big lookup table, right? So that's what FPGA is doing, and that is what Sora guys did, right? They had to go through this process manually for each piece of code to understand how to do it and so on. So here we claim the compiler should be able to do it themselves with a little guidance of you. There's no kind of, you can't really optimize everything. So the only thing here we would need to specify is that we want the loop unrolling to the level of 8 because we know our cache size and so on. The rest can happen automatically. So basically, so what the compiler then does, it goes to this code and says, okay, what are the input variables? So we have this scrambler state, and this thing, basically, so what happens in this code? We do this once, and then we return for the next piece of information. So if you look at that code, we do this and repeat it for every input, right? So the persistent state for this block is this scrambler state. So essentially, the scrambler state is the input to this calculation. And the other input to this calculation is this X thing, right? Which here is, is given through vect.xa, right? So these are the two inputs. This guy here is not an input. It's not an output because it's just the index and it's never seen anywhere out of there. This guy as well. This temp guy, again, it's actually reinitialized here and lost there, so it's not an input. So this is, again, the kind of analysis Sora guys had to do manually, so we kind of do it all automatically. And we calculate, right, okay, we have this state, which is this guy, which is a vector of 7 bits. And we have this guy, which is a vector of 8 bits, because that's what we decided. So the input space is 15 bits, right? So any input to this block, so the performance of this block, if I give it to you to run it, and I give you this 15 bits, you're able to execute this block without any help from me, if you don't see the rest of the code. So you just do it for all combinations of 15 bits, so it is 2 to the power 15, and the output you give me are 2 bytes, right? Because the output is these two states, right? Again, I need to output the scrambler state because that's something which repeats through this outer loop that I'm not doing lookup table over, right? This actually has to be both input and output states. So I have two 8-bit states. Well, they're not 8-bit, but overall it has to be 2 bytes. So I create a lookup table to the power 15 times 2, 64 kilobytes. And then when I actually execute the code, it is going to read from a lookup table. It's not going to run all this. And if you think of it, this is very expensive. A CPU will have to do 8 iterations, a lot of bit level operations. Instead of it, it is just going to do, it's just going to do one read from a lookup table. Right. And so the nice thing is now you have this abstract syntax tree. The compiler goes through it, looks for all possible expressions. Every single item in the lookup syntax tree, it will actually look for and do automatic lookup table. Right. So that's the benefit. However, you need to be aware how you write the code. I mean, it's not, you have to write the code in a sense that it could be optimized. This guy is simple to optimize, right? So here is an example of a code which is not easy to optimize. And the credit for implementation goes to Kun and Sora guys. We just kind of made sure we can capture these kind of optimizations through in Ziria as well. So suppose you want to do a permutation, right? So I have an input array. So there is a function permutation, right? So if I give you a set of indices, and then I give you an input array, you should permute them to read the corresponding indices. So for example, if I give you an input array 1, 2, 3, 4, so you should output first the 0 element, which is 1, then the second element, which is 3, then the third element, which is 4, and then the first element, which is 2. Okay? So it's a simple permutation. Now, okay, sorry, so in this, I didn't really assume, suppose the inputs are bit arrays, not byte arrays, because then it becomes difficult. Suppose this input is bit arrays. So unlike here, right? So the question is, can we make this a lookup table? Okay, it's a trick question. If anyone, okay, the question for you, could you think of how to make a lookup table? It's not easy. The hint is that these permutation indices are constant, right? So there isn't, you don't need to consider them as input variables, right? So the only input variable is this guy. And the output variable is this guy. However, they can be actually quite large, right? So, okay, it's difficult. I mean, I'll just kind of let you think about it. Basically, what you have to do is you can break this input arrays into small chunks, right? So if you think about it, as we had in the previous example here, the input, 15 bits, right? The size of lookup table is 2 to the power 15. It explodes exponentially, right? But the output is only 2 bytes. It's not 2 to the power of 2 bytes, right? Of 15 bits, right? So it's better to put things in the output and keep the input small if you can. So in this case, you still need to do this transformation. You have to write the code that way yourself because the compiler cannot do this high-level thinking for you, right? And only if you write the code that way, it could figure out. So basically what you have to do is basically, if you have a large input array, so you cut it into small arrays, binary arrays, and then the input is a small array, and the output is a big array, right? So this makes it possible because let's say this input is I don't know, like 8 bits, and the output is 32 bits. So you want to permute larger tables. So you will you keep this array empty, let's say all zeros, and you'll put ones only where you see where your permutation index tells you to put it, right? So then what you have to do is just OR these things together, and that you can do quickly. So basically what you do, you basically break this vector into subvectors, and you do a permutation of each subvector, but now you permute in a larger space. So instead of doing over this, suppose this big vector is huge, right? But you just take a chunk of it, you create it here. Take another chunk, you create another of these vectors, and you just OR these vectors, and you've done it in a much faster way than you do otherwise. So the key takeaway point here, I mean, we can discuss if you're interested in the details of how this is done, but the key point here is that if you want to do lookup tables, there are lots of places where the compiler can do it for you, but no compiler is kind of almighty. So there's no, you have to do a little bit of thinking for these kind of examples to make sure that, and if you don't do this optimization, you cannot have Wi-Fi running in real time, right? So, and again, all these credits for doing this optimization goes to Sora code. What we try to do is kind of capture these in a more general form. So if you write other kind of codes in the same way, you can expand it there. So these are kind of things you would need to do whatever programming, whether you do it in GNU Radio or you do it in Sora, if you want to do real time in radio and CPU.
Maybe it's not clear here because you still have to write how many over ones you have in the right places. The XOR that you do at the very end.
Right.
The number of writes.
So the thing is, if I give you this, I think I was too quick. So basically, if I give you this, and I say, I take this for I equals 0 to 8, and I write this guy in whenever the index of it is, right? So the input space is 8-bit, and this guy is constant. That's what I said as a hint. So if it's not constant, you can't do it. So this guy is constant. So my input to the whole block is just this. But the output is large. The output can be 32 bits, 64 bits, whatever you want. So my lookup table is going to be 2 to the power 8 times 32 bits, right? Which is not too bad. But if I put the whole 32-bit here, right? If I don't cut it in pieces, then I'm screwed. I have 2 to 32. That's 4 gigabytes, 4 gigabits. Whatever. So the key observation here is that you need to cut this input table and do you could have done it inversely, right? If you look at this formula, you could have said OR of I equals IR of PI. For the big one and put in small. That wouldn't work because the symmetry is the other way. So you need to figure out this trick. And then the lookup table is of this size. Now the OR is, or if it's 32 bits, you can do SIMD or it's really fast. So for every block. So it does buy you like 2 orders of magnitude. Any other? Okay, so the next potential of this kind of approach, which we haven't done yet, but we are hoping to do, is that now we are targeting only CPU architectures. And lots of things here are really specific for Sora and could be ported to GNU or whatever, wherever you have your CPU running it with a single core. Now, so that's what I call like symmetric multi-core, let's say multi-cores, multi-core Intel CPUs and so on. Now, other options are you can have DSPs, FPGAs, lots of small multi-cores. So it'd be really interesting to understand how can you map these things, if you can map these things efficiently to a core. The nice thing would be that you can write code once, and then you can run anywhere, right? And that would allow a research community to compare the code, to do benchmarking, to share the code and all that, right? So I think it's kind of, I like the idea because of that, and that was the motivation for the project, to try to kind of make this whole area a bit more coherent so people can, collaborate more closely in terms of code as well. So this is a kind of an interesting thing. And then the key problem here is you have different types of parallelism. You have data parallelism, pipeline parallelism. Then you have this thing like SIMD instructions. You have coprocessors. Maybe you have DSP. If you have a DSP block, you will have an FPGA, FFT coprocessor and decoder coprocessor and so on. So there are interesting questions there. How do you see in your code which coprocessor you can use and so on? So this is pretty much open question. So what we actually do is we support SMP, so symmetric multiprocessor machines like Intel multi-cores. We support pipeline data parallelism. I'm going to briefly mention it next. And we support SIMD. So this is something, again, you have on Intel CPU. So it's really like a mainstream platform. So the data pipeline parallelism, again, this is, we again borrow the low-level C code from Sora. But the interesting observation here is that we can really do something like this. So if you have this pipeline, you can just put a special operator, which put these brackets. And the compiler then will go and rewrite this into putting a queue on this side. So we'll say, OK, this is on one core, this is on another core. So on this core, I'll put a queue. And then on the other core, I'll put the other queue. And I'll just read this queue. And I do all the synchronization for you completely automatically, right? And so basically, I put this core to this thread to pin to core 1, put this thread to core 2, and give them real-time access. And I can speed up the things. Right, so there's flexibility there, and the pipeline parallelization is relatively straightforward. There are still cases where it's not obvious in Ziria, so this is still kind of, all this parallelization is still kind of work in progress. But there are lots of cases where we can do that. And we can use parallelization in Wi-Fi design to again, make it work as fast as we need. Right, so like this is a synchronization queue. So I want to give you a simple code example. So we talked about the, scrambler, right? So I just want to run the example with you. So it's the same code we saw there. And let me see how is that going to work. So this is our, it's a good start. Maybe I put it here. Scrambler, I think this is the one. Oh no, this is not that one. Okay, so this is a kind of the simpler code like Scrambler, but you can write anything. So the benefit is that now you can change your Scrambler, you can change the code you actually run, and the compiler will be able to do it automatically. So you should be, it's very similar to what we did before. It's some kind of state machine. I just typed in something, right? And so the key thing which we instrument here is this thing, which says, I know this is a lookup table, right? So you could maybe do it automatically. We haven't done it yet, but it's relatively easy for me to see, okay, I want to vectorize this into size 8 because I know it's going to create the lookup table. It's easy for human, it's difficult for a computer, so we didn't automatize it. But so that's the only instrumentation we put here, right? So now I'll just go and right, so so this is called, so I'll just do make of this thing so what I'm saying is I just want to dump the output so you can see how the compiler created this code. So what is the kind of optimization it did. And basically, if I don't give it any, this is the thing. So if I don't give it any, so I give it some input. I didn't give all the, sorry, I have too many examples, so I'm getting kind of compute. So let me see. Let me try to do it this way. So what I'm trying to do is basically I'm running this, and this is the amount of time it takes without any optimization. So if I'm, so the only thing I need to do to make it optimized is just put two switches. So basically I just added this vectorize and auto loot, and then something is wrong with this. I think the other examples will work better. Sorry for this one. I kind of changed so many. So basically, what I want to show you is difference in the performance. But okay, at least I kind of showed you that. Okay, this is the type of code we can run, and the annotation we have to add there. And I'll have more successful demos afterwards. So sorry for this one. I think it's the other ones I practice more. So okay, coming back to the Wi-Fi, basically we had so this is the kind of performance evaluation we did. So we re-implemented the entire Wi-Fi, we ported the Sora code, and again, the algorithms that we used are the ones they did in Sora, and pretty much the optimizations are kind of similar. The only thing is that the code is very simple, and all the optimizations are detected automatically, right? So the same nature of optimization, but they're all done automatically. So so here I'm giving you all the receivers, right, at different rates, and then this is the throughput that is required in megasamples per second, right? So it's somewhat basically here is what Sora does. Here is what we can do, and this is this is basically the Wi-Fi requirement, right? And so we do lose a little bit, right? But basically we get much easier to write code, right? So there's much less you have to worry about. So we lose, I guess, I don't know, 20% or so on the transmitter side. And so these throughputs, right, are mega samples per second, and each sample is complex 16-bit number. And so we get like mega, so four times this bytes per second. So it's a kind of quite high speed. And in all cases, we kind of meet the Wi-Fi requirement. So even though we lose a little bit on performance, we can still comfortably run Wi-Fi receiver at 40 megahertz. And this is on the transmitter side, right? So here we are possibly not as efficient in doing lookup tables because they can do that manually, and we discover in the compiler. But nevertheless, we kind of, so these are again the requirements. Now here the requirement is basically you have a constant stream of data that comes in, 40 megabits per second. No matter what your rate is, you need to process data in 40 megabits per second. And down the line, you'll trim out something and you will have a lower processing rate. So that's why the requirement is constant here. On the transmitter side, right, your data input comes at a rate which matches your transmit rate, right, because it's bits per second. So if you're sending 6 megabits per second, you need to feed in 6 megabits per second. So we are able to process, again, way faster than that. And again, this is even when there's a bigger difference with respect to Sora, but this is because it's suboptimal when discovering lookup tables and unrolling them. But again, we have a flexibility. We don't have to do it manually. It's all fully automatically done. Right? So another thing we did the kind of an LT-like demo. So it's not a full implementation of LT. So we had the resource blocks. We were able to populate the frame, put the reference signals, the PSS, SSS, and send these subframes and kind of create this grid. And then we do some random encoding of packets inside. So we have the basic signal search in there implemented and so on. And we had 2 Sora boards. We didn't do it on very large distances, but basically we were able to write completely new Ziria code for LT receiver without even, just from scratch without copying anything. And we were able to get a real-time performance at 20 megahertz already, right? So there was no extra optimization needed. It was really kind of just developing the algorithm. So I was quite happy to see that because it was a completely new project where we had to really design only the algorithms, and we had really spent very little time dealing with all the other optimizations which you had to do in any other tool. So I kind of was quite happy with this kind of experimental result as a programmer. So this is the last slide about Ziria, and next I'm going to move to Wi-Fi. So we did the basic cell search. So we did the things inside. We were cheating. We used Wi-Fi encoders because we haven't implemented, right? So we have all this grid, and then we do random. We just pack packets in there, but it was easy because the Ziria is very easy to interface, right? You just it checks the types. You just put it in. It does all the vectorization for you. So we literally took the Wi-Fi encoder, plugged it in there and said, okay, we'll encode our packet in the whole area. And it just worked. So but it uses, I don't know, QPSK 1/2 coder from Wi-Fi on the top of it. So there is something. We get data through, right? So it's released to GitHub under Apache 2.0, so you can download it. We are hoping to very soon have a demo where you can just take the code, take the Wi-Fi. You need Sora boards. You plug in your 2 Sora boards, and you get your Wi-Fi code running immediately, right? So that's the goal. We have a few demos coming up, so we have to get this ready very soon, right? And this implementation is including release, and pretty much the things I'm going to discuss next are from not the exact code from the release. It's kind of adapted to showcase the things that are interested from Wi-Fi design point of view, but they're kind of the same algorithms and the same ideas as they're in the regular Wi-Fi. And again, this is the algorithm design comes from Sora. We just did it much simpler and much higher level, right? And so essentially at this point we depend on CPU and SIMD. SIMD vectorization is done by a programmer, right? So we made it easy, and you'll see we made it easier to write vector operations in SIMD, but you still have to do that manually, as you have to do other stuff like this lookup table things. Some algorithms will not be able, you cannot do by a compiler, right? You have to give some thinking, but it's relatively like this permutation algorithm we now give as a library function, so you don't need to worry about it. You just call this permutation, it will do this for you. And then we're looking into porting for other CPU-based things. Okay, so we're coming to the case study of Wi-Fi design. So here, basically I want to go through the basic Wi-Fi design block. And so, so motivation here is that what I see in the community is that the wireless architecture and design people are looking at the two communities that are looking at Wi-Fi architecture and design are fragmented. So you have lots of EE guys who consider lots of physical layer, do a little bit of Mac, but they rarely go all the way to building systems, looking at the application layer issues, running TCP, understanding, going all that way, right? And then you have a CS guys which start usually considering from Mac and above, and they go from the high level and they try to hack all the way they can, but they stop pretty much, they hack the firmware and so on. I mean, there are obviously exceptions, but it's just like this is the kind of general feel. And so I think one of the reasons when I talk to people about it, I say, why don't you, give to your students software radio to try to kind of implement everything all the way? And they say, oh, it's too easy, too difficult, they can't learn all that. And it's true, right? If you want to program, if you get an FPGA radio, you can spend a year of your, 3 years PhD, if it's a short one, just learning how to start anything. And then you need to learn how to program the thing, you need to learn about the optimization you have to do, and you need to learn about signal processing things, and you need to have your own ideas, and all this stuff. So you're just overwhelmed with the things you need to learn. And so basically, the goal of this is to try to remove some complexity and then give this to a PhD student who can then use it and say, okay, well, I don't need to worry about lookup tables. I need to worry about cores. I don't need to worry about real-time pinning to a core, real-time priorities, vectorization, all this stuff. It should be taken away. So the actual burden of a student is just to do some algorithmic research and try it out. So this is the goal, right? How far we've gone, we'll see. But so then we have hopefully some opportunities for synergies. And the other thing which is important for me is that you're able to build bigger platforms, right? So basically, when you could build the code, for example, inside a group, you build a piece of code, the next student wants to pick up. Well, pretty much from the code you have now, it's kind of impossible. I find it difficult to use my own code in the next project, let alone somebody else who is less experienced in working in this area, picking up a code, and it's just very, very, very difficult. I mean, those of you, I guess, who work with it have this experience. So really, this is kind of trying to facilitate wireless design in a way that open source community have done for, MapReduce or this kind of Hadoop or these kind of things. You can actually build bigger systems, compare, and so on. So it's a big goal, but at least this is a kind of step there. So let's see how far we can go. So why is this interesting to do synergy? So, there's a lot of people who think, okay, we have these layers for reason, Mach and Phi, and so on. There are lots of interesting examples. Some of you might be there. I think maybe they mentioned some of them last week. It's basically that it's not about having spaghetti design where you can do everything, physical layer, the upper layers, and so on. But you can rethink the fundamental layering of the wireless. And there's several good examples for that. So if you think about hybrid RQ or rateless codes, right? So that wasn't there. In Wi-Fi, you don't have hybrid RQ. So basically, and you can't really implement it because that's the way Mac is designed. So there is no notion of being able to keep the packet. Now, okay, in LT you do have it, but that comes with a whole new thing of standards, right? So is there a reason not to put some of these things up front as a separate blocks which people can change and use other stuff and then build a Mac upon it with assuming different underlying API? So basically similar like rateless code I think you heard about last week and so on. Then so here's the correlation detection. So we've done some work there as well, and so I think in the morning talk you heard about the inefficiencies of AAC and so on because of these detection issues. So the problem is that this is not really exposed to the medium access control, right? So you could maybe have a different parts. So what you have is just energy, whatever, some CCA procedure, right? So you don't know if it does energy detection or it does correlation, what level of correlation it does. So all these things are hidden because I think let's be kind of very generalizing. CS guys usually don't understand that, so they just like this abstraction of channel is free as channel is empty, right? But if you provide an abstraction that say, okay, I have some readings, some correlation, something that you still need to think of. There's lots of information there. You can't just give the sample, the whole waveforms, the INQ samples to the Mac because it's too much. But you can give some other details about the signal. And there's lots of you heard about correlation detection in the previous talk, right? So you can give lots of other things potentially to a designer to deal with it, and then so to address this huge inefficiency. Right now, you pretty much your hands are tied. You can't do anything. You just have this CCA, which is giving you yes or no, right? And then, okay, the other thing that I've been working on before and other people are working on to use channel impulse response, for example, for localization. These are just 3 random examples, pretty much. So if you have a channel impulse response from a channel, you can do much better localization for Wi-Fi than if you just have an SNR. Because SNR is some kind of aggregate, and it won't allow you to deal with multipath and other stuff. If you actually expose this channel impulse response, it becomes way easier, and you get much more information. The localization is more accurate. And this is not very difficult. I mean, even some of the Intel cards kind of accidentally expose it. So you just get it from a header. You don't need to give me all the INQ samples, right? You can just give me the ones from channel estimation, and I can do lots of things with it. Or, I can do maybe cognitive sensing with that as well, right? Some kind of cognitive sensing. So there are lots of things you could do if you're able to rethink these kind of designs and not have such a hard line between a Mac and physical layer. So so one of the goal here is that if you are able to come up with these blocks, and hopefully that's going to be maybe your future research, come up with different physical layer blocks that are useful for the system builders afterwards, right? With the right abstractions, with right algorithms, the whole networks will be faster and more efficient and so on. And so the goal of the tool is kind of help you do that. So I mentioned some of these. Basically, phi level is in Wi-Fi. Phi is standardized. You cannot really change it. You have to feed the pipes in the bits in the data pipe. You get your bits out, and then you can just do tricks like, okay, you might change the Mac. You can just get the data even with errors and try to read the bits with kind of hard decoding and do some post-processing out of it. But it's a very kind of solid, very well-defined API between the Mac and Phi, which you can't really get in. And people do lots of innovation on the Mac layer. So there are people that redesign the firmware for some cards. You can write your own Mac and so on, and lots of interesting things coming out of there. But still, because of this interface to Phi, there's lots of innovation that cannot happen. Some of this I mentioned there. People do it in software radios now. So for cellular, it's kind of even worse because you pretty much you get your dongle or your phone, and you can just get data out. You can't even change the Mac. The base stations you can't even touch. So it's very difficult to understand the scheduler inside and all this. So the only innovation you can do is try to go from the upper layers. And for example, what people do is try to figure out, okay, so when is the base station going to wake me up again? So I'm going to learn that pattern, and I'm going to save my energy by optimizing for that. So you get very, very little information. So again, if you had more information there, and if you have a different design, you could be able to do that. So you can experiment with all these things with software-defined radios. So that's a kind of, and then if you have a good ideas and good prototypes, hope is that could become standard one day. So, so what happens in reality, and a lot of people kind of, it's not a new idea. I mean, people have noticed that if you look at most of the wireless designs nowadays, they have lots of standard blocks, which if you go to if you try to design anything in a DSP, when these DSPs are already equipped with correlators that with coprocessors that do these things fast. So it's so if you look at these standard blocks, right, there is no reason why some of these wouldn't be exposed to you as a network designer in a smart way, right? Not just giving everything, so that you can actually build network from these standard rules. So you have to expect maybe some certain ground rules, but you can redesign your Macs, and you know you can do all this kind of crazy stuff in there if you want. So okay. So now I'm trying to basically assume that you are very interested in this topic, right? And you want to jump into doing this kind of cross-layer design, and you want to build your own system, which you want to evaluate on. So the first thing is how to design a wireless transceiver. Okay, so you don't know much about it. For example, you know some basics, but actually, I think even if you know signal processing, there are lots of small tricks which are not really rocket science, but you kind of need to learn and understand. It's kind of mixed of I guess industry experience and experience of designing these things and what hardware can do and so on, which are kind of decided and decide on the transceiver design. And so here, basically, I'm just taking one part, and again, I'll use most of the algorithms from Sora because they've already done it very nicely and it works in real time. But so basically, okay, first I want to touch on challenges on the. So the issue is performance. Obviously, you want to do it. You want to do it real time on the line speed. The second thing is complexity. You want to have a flexible system. So these DSPs are very difficult to program, and even though they are very low power and so on, you don't probably want to experiment with them because that's not an experimental platform. And then the other thing, if you want to, if you want to commercialize something, then you don't need to worry about the cost of these things, about the patents. So there are lots of stories from the industry. For example, LT has lots of patents there. So if you're selling an LT chip, you need to be aware that you'll have to pay I don't know how much dollars for every chip for the patents. Or if you sell Wi-Fi chip, you don't do that, or GSM. The other thing is also I don't know who owns now patents on OFDM, but for example, there was, I remember back in the days of ultra wideband. So Intel was pushing OFDM ultra wideband only because they only had a receiver and transceiver in ultra wideband. So for them, it was cheaper to build it in OFDM, regardless of whether it's a good technology or not. So there are all these things in the industry. So it kind of it's difficult to understand what is the kind of best thing. I'm not trying to answer all these things. I'm just kind of trying to give you one idea of how to choose your design, right? And how you can make this initial design from where you can actually learn, experiment, change a bit of some blocks, and see what you can do with the whole network. So that's the kind of goal of this, the remaining of the talk. So, okay, the first thing we have to ask is which physical layer we'll use. There are lots of them out there. And so, for example, I mean, CDMA is still widely used, and there is OFDM. So the question is, which one do you use, right? So we will use OFDM because it's the one we have, but okay, there's a better reason than that, I think. So the CDMA, basically, in a nutshell, it uses random codes, pseudo-random codes to combat multipath. So you take your symbols, modular symbols, you scramble them with these codes, you send them out. So the pros is that it's not as complicated to implement, and but it's difficult to equalize over wide spectrum. So there are different trade-offs you can do with in there. Now the OFDM is a different way. Basically, it uses subcarriers, so it uses frequency domain instead of code domain to deal with multipath. So it has great robustness and less complexity, but actually it's more difficult to implement for simpler receivers. So, and it can achieve higher spectral efficiency. So pretty much the rule of thumb I've heard of is that if you want to go for very low power, low rate receivers, you should go for CDMA or other kind of things. But if you go above 10 Mbps or so, you're safe of using OFDM, right? So that's why most of the today's, I think I have it there. Yeah. So most of the today's PHYs are using OFDM anyway. So I think it's kind of a safe bet to assume that's the kind of thing you want to experiment with. And so in particular, Wi-Fi, LTE, WiMAX, then the new 60 gigahertz are also proposing OFDM. What is the reason? Again, I think it's definitely a good technology. It's difficult always to know whether it's because one company has patents in there, so want to push the standard and they're strong enough, or But it works fine. So the other example is OFDMA. And OFDMA is a variant of OFDM, which is essentially the basic principle is the same. The only thing you do is multiple users can share the same OFDM symbol, both uplink and downlink. So, and then you can do max scheduling at symbol level and so on. So that's an interesting example of what I've been mentioning before. So if you think of it, to some extent, OFDMA can be seen as a kind of a mix of physical layer and MAC. And if you look at the LT specs, it's not really clear what the MAC is, right? You have this scheduling of resource blocks, but they're happening pretty much at the physical layer. And then you have to do time synchronization at different levels. So this distinction really in the modern cellular system is very blurred. And when you talk about MAC, there's a lot of confusion when you talk about low-level MAC or higher level MAC and so on. So this is an example of this kind of synergy in my mind that coming to there. So basically, but the bottom line is that if you're thinking about OFDMA, most of the things I mentioned here really hold, because you need to do a proper signaling and channel pilot estimation, all that already before you start doing the OFDMA processing for taking out different users and so on. So this basically the basic things here really apply to most of the to most of these things to what I'm going to talk about anyway. Right. So so I'm going to give you an overview of a transmitter, and then just give you a brief discussion of what each block is used for. And for some of the blocks, I'll demo. I'll try to run the code and show you the output and give you an idea how what kind of things why they're used. So there's lots of very nice math behind all this, but I'll avoid any math now because I don't have enough time, and it takes much more time. So this is really almost like an experimental session where I'll give you a very high-level idea with simple examples why you do OFDM the way you do, right? So of course, if you're interested, there are lots of nice books where you can read about it. It's a basic wireless system design. The other thing is also some of the things I'll discuss is actually how do you do this efficiently on a CPU, how you can do it efficiently on Sora, in particular the implementation we have in Ziria, which again should be portable to most of the GNU radios, Blade RFs, and all these systems that use CPUs. Right. So here is the baseline, basic transmitter in a nutshell. So, and I'm giving it in Ziria code. So all these the functions which we implement separately, but this is really copy paste from the implementation. So first thing we do, we create an STS symbol in time. STS symbol is the preamble. So this is a fixed set of INQ samples that you're going to set. So you create them ahead of time, and you just say, I emit this on the air. And the next thing I do, I emit my LTS. So this is the first part of the preamble is the thing you use to search in time for your packet. Okay, and then the second thing is the thing you use to estimate your channel. So basically, once you found your packet, you use this to do equalization, and I'll talk about it in more details afterwards. So this is this is with semicolons means I do first this, then this, and then I do this big bunch of things, right? So what I do then, I have a packet. So packet comes in here, right? So these guys are executed before the packet even comes. So that my data starts coming in here, and I do the CRC. So CRC, and this is the thing I like about it, it was one of the design goals of the language, is we clearly see what are the shared states. So the CRC depends only on this parameter here, and this is coming from the header, which I omitted for clarity. It should be a header processing before this, right? But there's a clear sharing of parameter. You exactly know what happens here, right? There's no other shared state except for this. So, why do I put 216? So this is the padding thing. Because you're sending these OFDM symbols, and we'll talk about OFDM symbols in a moment, you need to make sure if you finish in the middle of OFDM symbol, you cannot really send half of OFDM symbol. To create an OFDM symbol, you have to have full OFDM symbol of data. So we just make sure with this padding, we are adding, whatever we send has to be a module of 216. So if we stop at 100, we have to add another 116 dummy bits to make sure we send the exact number of OFDM symbols. Then this thing is getting scrambler. Then it's getting encoded. Then it's getting interleaved. And then it's getting modulated. then we add pilots, we do IFFT, and then we send. Okay, so again, this preamble detection was with preambles for channel detection and estimation. So the CRC, the basic idea of CRC, when you do all this to the receiver, you look at the packet and you look at the CRC. If your CRC is wrong, you throw away packet. You did the best you could with your packet decoding. You couldn't decode it, okay, so you throw it away. Now, the scrambler, it prevents high peaks in the data, and I'll show you that. If you have very kind of too smooth data, like have all zeros, it could create some problems. We'll see later. And so basically, you want a scrambler to avoid this kind of very too obvious data patterns. And then you do coding. I suppose most of you know what the coding is, but basically, okay, in a nutshell, you send more bits so that at the receiver, if some bits are corrupted, you can do some clever algorithms to get the information out. Okay, then interleaver. So the basic idea of interleaver is when you send your code out, there will be, and you send in frequency, there'll be errors somewhere, right? Maybe your channel is bad in some cases, and usually these errors are correlated. If you look at a channel, it will have like a deep fade, and at some point, so if you think about it, if you lose some bits or if you have bad information about some bits, they'll be very local, right? So here you do some kind of random permutation at the transmitter. So to make sure the bits, when you decode them, the bits that have local errors are going to spread all out. And that's simply the nature of the codes. The codes can deal better with this if the errors are not local, because codes are operating locally. So it's really a kind of a technicality, but quite important, right? So modulate, basically, it's just the regular, usual thing. You take a few bits and you map it in this constellation thing. I'll show one, but I believe you all heard about that anyway. You should know a lot about it. And then you have to add pilots, okay? So we'll see also what the pilots are used for, but basically they're used to track all the inefficiencies and problems with the receiver. So the fact the channel is constantly changing a little bit, and also your clocks are skewed, and all these kind of imperfections in the signal, it can be corrected with these pilots. And then you do IFFT, and we'll talk about FFT and OFDM in a bit. But basically, this is kind of the final block. We'll explain a little bit later. Sorry?
So this transmitter, if my assumption is this 1x1 type of transmission, and if I am using some kind of MIMO, then this sequence will have different blocks?
Yes. You can add different, yeah. We haven't implemented MIMOs ourselves. I'm sure it can be done, but you can put more, yeah. This is all the code. You can put more blocks inside and so on.
And that's how we have to do this?
Yes. So I don't know if you want to add in here some pre-coding or whatever you want to use. But this is, the code, and I'll show some of the code now. So okay, so one of the things I wanted to show is like basically what is the OFDM. So what is the point of OFDM? So I guess, and also show you a little bit of demo how you can do that with the code. Let's see. I'm hoping I'm going to be more successful now. It should be. So this one is in Wi-Fi. So I have a lot of code here because I don't want to write it in front of you. I just want to kind of uncomment what I want to show you and then run it in front of you. So let's see. I'm first going to run this one. Okay, so what am I doing here? So if you look at this bit of code, so basically what I'm doing, I'm going to do take some bit input, and I created some random bit input. I'm going to modulate the bit input. Okay, and then okay, so I want to illustrate what the OFDM is doing, what the IFFT is doing in this case. So I want to modulate this bit input, and then this block, what is it doing? It's actually it's cheating. It's just taking one bit of the output and then emitting lots of zeros. So what I'm going to do, basically this C0 is a complex zero. So I kind of emit only one input from the actual signal and lots of zeros, right, to just create a simple sign, what OFDM would do. And then I do IFFT, right? And then I plot this. It's okay. So it's kind of as simple as that. And so how FFT looks like, this is the one we're using now. Okay. So it's, okay, this is the Sora IFFT implementation. This is a plain FFT, nothing special about it. So what you do, you basically say, first of all, I zero out these things. I don't really have to do, but I think it's remained from some other part of code. And then I say take 64 elements, they're complex 16 numbers, do the FFT and emit. Nothing more than that, right? So now I'm just going to run this code. And while I'm running, I should get this other guy ready. Oh, where's my mouse? There. Here it is. So this is actually Sora visualization. What happened with my okay, I think I have to do it once again. So I'm just running, I pre-created this make file. They're just running a sequence. So what I'm doing here, I'm running this compilation from Ziria to C. And then what I do, I run this. This is a Visual Studio compiling from C to exe file, and I just run this on a file. Okay, and so now I can use this Sora debugging tool. Okay, now I need my mouse back here, right? I'll just how do I delete this one? I don't know. So mouse keep escaping. There it is. So I can look at this thing. Okay. So what I have here. Right, so what did I do? I basically created one sine wave, okay? And so why did I create one sine wave? Because I take a vector of inputs, and I basically put put a 0 in there. So what FFT is doing is it's taking my vector, is doing transformation in the frequency domain, right? So it's summing lots of sines, right? So I guess you're all aware of the FFT as a signal processing, right? But basically what it means is that if I take a vector which has all zeros and one symbol, right, it's just going to give me a sign, right? And so that's what I created here. And then I can create another sign. So the interesting, okay, it's a sign at one frequency, right? So if I give him, so here I created a code that is doing the same thing. It's just non-zeroing the thing at a different frequency, right? So now it's kind of sending a symbol 0, and this was sending x0 and complex 0, and this is sending complex 0 and x1, right? So it's just a symbol at different frequency. And so if I run this one, then we'll shortly see. Okay, so it's just a different frequency, right? So every symbol is representing a different frequency. And what modulation is telling you, so the actual symbol you're sending, is where is the starting phase of this thing, right? So if you change the phase, it's going to move up and down. But you're sending a simple sign, okay? So now, what happens if you just send two symbols, right? These two signs together at the same time. So now, I was taking two elements and sending only first one and 0. Here I was sending the second one and 0 and the second one. Now I'm going to send both elements I took, so I'm summing up the two. So it's really just the sum of these signs, right? So it's the compilation is slow, not really the. What's going on? Okay, so now so I have just a simple, a mix of these signs. So actually you can see that, so if you do your FFT, you see some crazy waveform. The reason why you see this crazy waveform is because you keep sending these signs, right? And they just simply sum up in the different ways. And so at the end of the day, so I think I have a thing here as well. So basically, this was the point we were sending in the first example. So there's a modulation here. And that basically means where is the starting point of this sign, right? And it's a sign at one frequency. So the starting point of this sign is a different modulation point, so it's a different frequency, and you just simply sum them up, and you get a second sign, right? And if you but this means I have a vector with all zeros in my IFFT, and I put just two symbols in there, and I get just 2 signs. If I put lots of them, I get lots of signs. So this is my random arbitrary IFFT thing, right? So if you think of it that basically because you do IFFT, each of the symbols is traveling, is modulated on one subcarrier, right? Or on one sign, right? So it's kind of a narrow band transmission on each sign, but you are actually superposing them together. So that's the kind of, so you can actually control which symbol goes on which frequency. That's the idea. So now that's the IFFT thing, right? So that's what happens when you do IFFT. Now, how do you actually do it in Wi-Fi? So you take your thing here, your data packet, right? And then the first thing you do, you actually have to add these pilots. So we'll explain in a second what the pilots are for. And then you basically do your IFFT. So if you wish, so usually the way people represent this, the y-axis is the frequency, right? So you put your signals in frequency. Now you can't send in frequency, send it really in time. So you have to do this IFFT to convert this in time, and you get this funny waveform that we got before. And that's something you send on the radio. But before you do that, you have to add a cyclic prefix, right? And so we'll explain a bit what the cyclic prefix is for, right? So that's kind of adding the cyclic prefix. And so maybe we can stop now for a break, and then I think is it now? Yeah. Okay. And then we'll follow on afterwards. This is a fair comparison, the same kind of architecture, right? So we use 1 core, they use 1 core. We are also, both of us are better when we use 2 cores, but we are still slower, right? Really the difference is because, for example, the main difference comes from mem copies. And we are optimizing that, you're still improving because, they know where the signals are going to. And so they can avoid lots of mem copying there. But we don't really know, we can never fully understand the code, right? So, for example, if I give you a data block, whether you're going to modify it or not. So semantically, you're not, from the compiler point of view, you're not supposed to modify it. So the way I do it, I copy it, and I give you a copy, and I know you're not modifying it. But if I give you the pointer, right, I don't know whether you're modifying. Sometimes in my analysis, I can figure out that you're not modifying it, and I'll detect it, and I do a pointer. And we don't really do that yet. But they know it because they had optimized everything, right? But that means your effort is much bigger. So, I mean, I wrote all these examples in half a day, all that you're seeing today. And I would like to see anyone writing these examples in Sora. Well, you have their code, right? Okay. So if you call an expert in Sora, it will take much more than that.